Hello everyone, my name is Wang Junnan from the Information Engineering Research Institute of the Chinese Academy of Sciences and the University of the Chinese Academy of Sciences. It's my honor to speak here and I'm glad to share my topic with you. Today, I'd like to talk something about how to crafting adversarial example to bypass flow and machine learning based botnet detector via reinforcement learning. I will introduce our work from the following aspect. First, motivation. Botnet attackers are looking for methods that allow them to bypass detection. For example, attackers use application layer protocols or external web services for C2 communication to bypass the firewall. They can frequently change the IP address corresponding to the domain name of the C2 server to evade IP and domain blacklist detector. And they also can encrypt C2 communications to avoid payload-based detector. However, these evasion methods cannot bypass the widely used flow and machine learning-based botnet detectors, which distinguish malware traffic relying on the statistical characteristics of flows. Moreover, these methods require extensive or complex direct source modifications, thereby placing high demands on attackers. Our one directed way to bypass the machine learning-based botnet detector is using machine learning's vulnerabilities to attack machine learning direct detector, that is, adversary machine learning. Our challenges including the following points. First is black box. That means we cannot obtain any prior knowledge of the machine learning detector. Second, in order to directly generate real traffic, we tend to implement an end-to-end attack. That means we should first keep the malicious functionality intact in the perturbed sample. Second, we cannot destroy the file structure and the network protocol structure of the PCAP file. Second, we should ensure the internal consistency of the features vectors. So we use the Markov decision process to model the problem of crafting adversarial botnet flow samples and implement general black box attacks via reinforcement learning. Our task is training the agent through a series of interactions with the botnet detector so that it can learn how to craft adversarial botnet flow example to bypass the botnet detector. Generally, our system setup is composed of two components, an agent and an environment. The agent receives feedback from the environment and then selects actions from the action space to modify the botnet flow according to the RL algorithm. The environment mainly included two models, a botnet detector and a state generator. The botnet detector is the detector we want to bypass. Its task is to predict the malicious traffic in the loop and feed the binary result back to the agent as a reward. The state generator is used to generate a distribution of the current sample state and help the agent to make action decisions. When the system starts to run, the state generator generates a state as based on the input sample. Then the agent receives the state and starts an action from the action space to modify the botnet flow. to according to the algorithm. Then the modified sample is input into the botnet detector, and a prediction results is obtained. Next, agent receives a reward according to the binary feedback, and the state generator generates the next state according to the modified sample. This loop continues until the detector is successfully misled or the number of the operations reaches the upper limit. Considering that our action space is not continual, we choose two classic value-based algorithms to compare which is more suitable. There are many differences between DQN and SAS. First, on policy, SAS learns the Q value based on the action performed by the current policy. While off policy, Q learning does so relative to the grade policy. That means DQN is broader, while SAS is more conservative. Second, under some common conditions, they both converge to the real value function, but at different rates. Q-learning tends to converge slightly slower than SAS, but it has capability to continue learning while changing policies. For the above reasons, we implemented these two algorithms and evaluated their performance through a series of experiments. The action space include a series of modification actions for botnet flow to determine which features should be disturbed. We refer to many works on machine learning-based botnet detector. We found that researchers tend to extract some discriminative features based on the working mechanism of the botnet, and these features often have high degrees of overlap in different jobs. Taking the difficulty of action designing into account, we chose 18 features that commonly used in the botnet detection. This feature shows the box plot of them in our dataset. We can observe that there are indeed some difference between botnet and normal flows. Based on this discovery, our action space includes 14 actions which can affect the above mentioned characteristics of transport layer by simply modifying the packet timestamp or adding carefully constructed packet. When constructing new packets, we mainly consider three attributes: timestamp, direction, and packet size. These 14 actions are divided into 5 categories according to the objects they intend to affect. To describe the state of the current botnet flow samples, we use the feature encoder with a deep structure, stacked autoencoders to extract the botnet flow features and feed them back to the agent as the state. Superficially, we take the first 1024 bytes of each botnet flow as an input for the SAE model. After training, it can learn a 256-dimensional space vector of the botnet flow. As for comparison, we choose two detection models in our experiments. A composite deep learning detector combining CNN with LSTM and non-differentiable machine learning detector based on ChatGPT Boost as our botnet detector. As for As for dataset, we select 10 botnet families from CTU and ISOT public datasets to form a new dataset and perform data processing progress that contains 3 steps as shown in figure 7. As for the experimental results, we evaluated our method from 3 perspectives. First, evasion performance. The evasion rate illustrates the probability that the botnet flow adversary example can successfully evade the detector. Table 4 compares the evasion rate of 4 systems after training on 10 botnet families. From table 4, we can find that the evasion rate varies vary among different botnet families. Storm family even has an evasion rate of 0. Through analysis of each family sample, we find that the lower evasion rates may be made due to the sessions containing the largest numbers of packets. So the effect of adding packets or changing the time steps is relatively small. Alternatively, the characteristics of botnet samples are very diverse from those of benign samples, causing the agent to fail to convert it into a benign sample within a limited set of action number steps. Construct between agents. In most cases, the SAS agent performs better than the DEQN agent. That may because SAS is an on-policy algorithm that is more cautious than DEQN. Contrasts between detectors, as shown in table 4, the evasion rate with chargeable as the detector is higher than that with bot catcher in most of the botnet family's results, and we believe that is because actions have a greater impact on statistical features than image features. Second is time performance. From the perspectives of the botnet families, the time performance between different families does not change significantly, meaning that as long as our agent is well trained, it will have a better performance than that of the baseline, regardless of what botnet family it deals with. For the perspective of the RL algorithms, the agent equipped with the DQN algorithm often requires more steps to bypass the detector than the agent equipped with the SAS algorithm. From the perspective of the detector, the number of steps required for the agent to bypass bot catcher is higher than that of charge boost, meaning that the agent need more iterations to mislead bot catcher than to mislead charge boost. Last is dominant actions. Dominant mutations refers to the most frequent actions taken by the agent when successfully evading the detector. Each botnet family has its own unique features, so the flows of different families also differ in terms of certain characteristics. Therefore, we guess that the influences produced by different actions should be different from each family. So each bot family's dominant actions should be different. From table 6, we can find that there are large differences in the distributions and the dominant actions of different families. And these are often related to the characteristics and the main functions of different family flows. Therefore, we determined that the influences of actions on different families are closely related to the statistical characteristics or image characteristics of each family. That is all my presentation content. Thanks for learning.